A Brownian motion, or also called a Wiener process, and usually indicated by capital B, is a stochastic process which fulfills the following three properties. First of all, the increments must be independent, so if t1 is strictly smaller than t2, smaller than t3, and this is strictly smaller than t4, then if you look at the random variables of the differences, so bt4 minus bt3 and bt2 minus bt1, these two random variables are always independent. So this means that if we look at the difference bt minus bs, then these random variables, they are independent of the past history. So if we take bt minus bs, this means that s is the smaller time index, and it means then that bt minus bs is independent of everything what happened in the Brownian motion before time point s. Secondly, we need to have Gaussian stationarity. So for any t larger or equal than s, the difference bt minus bs will follow a normal distribution with mean 0 and with variance t minus s. And then finally, path continuity. We start at 0, so b0 is always equal to 0, and all the paths of the Brownian motion have to be continuous. Such a standard Brownian motion is a Gaussian process, and it is the only Gaussian process which has continuous sample paths and for which that the mean function is equal to the zero function and the covariance function the minimal function. So the expected value is always equal to 0, and if we have the covariance function kst, so the covariance between bt and bs, this is always the minimum of s and t. Furthermore, a Brownian motion is a time-homogeneous strong Markov process. So this will mean that for any finite stopping time tau and every t value larger or equal than 0, the conditional distribution of b tau plus t given bu u smaller or equal than tau is equal to the conditional distribution of b tau plus t given b tau. So my conditional probability on all the states up to moment tau is the same as just a conditional probability when we only know what happened at moment tau. So the only thing that's important here is the Brownian process at time point tau and not everything that happened before. We can then also extend the Brownian motion if we have a process x, a stochastic process x, such that x of t is mu times t plus sigma times a Brownian motion, then this process x is also a Brownian motion, and it is called the Brownian motion with drift mu and diffusion coefficient sigma squared. And then if we have d independent Brownian motions, so we have b1 up to bd Brownian motions which are independent and defined on the same time points, then we can combine them together in a d-dimensional Brownian motion in such a way that bt is just a vector b1t up to bdt for every time point t larger or equal than 0. To then generate such a Brownian motion with drift mu and diffusion sigma squared, we will use algorithm 5. So we start with a set of time points t0 up to tn. We generate as many standard normal distributed values, and then we see a double for loop. The inner for loop will create the standard Brownian motion. Standard Brownian motion based on the fact that the differences are independent and that they are normally distributed with a mean 0 and a variance of t minus s. We can write btk as btk minus btk minus 1 plus btk minus 1 minus btk minus 2 plus and so on until bt1 minus b0, because we know that b0 is 0 anyway. Each of those differences follows a normal distribution with mean 0 and variance equal to the difference between the time points. So multiplying these values for a standard normal distribution with the standard deviation from these differences between Brownian motions, so the root of tj minus 1, we get the normal distribution with a variance of the difference. And then we sum them because we have a sum of all those normal distributions and we know they are independent. So this inner for loop will create the Brownian motion as such, the standard Brownian motion. And then the outer for loop will change this standard Brownian motion into a Brownian motion with drift mu and diffusion sigma squared by just applying mu times Ti plus sigma times Bti.